Hello, I'm Michelle Munk, the Entry, Descent, and Landing Systems Capability Lead. This video accompanies the Envision Future Priorities package for the Land Thrust entitled Entry, Descent, and Landing to Enable Planetary Science Missions. This Envision Future is focused on entry, descent, and landing technologies that can enable spacecraft that are entering or transiting planetary atmospheres and/or landing on the surface of bodies all across the solar system. What we're really trying to do is enable or enhance missions from small spacecraft class all the way up to flagship class. On the left, you see some examples of our investments that are doing just that. We rely on entry systems modeling and testing to mature and validate our models that can reduce risk, improve science return, or reduce the cost of these missions. Some examples on the left show you a desktop wind tunnel or parachute modeling with computational fluid dynamics, some of the new facilities that we're investing in, such as a magnetic suspension wind tunnel that removes the effects of the sting on a model. We've also invested in different hardware technologies, such as new materials that reduce part counts or improve performance. And we do everything that we can to mature those up to the infusion point, such as building scaled prototype models that can demonstrate how we would integrate these on a real science mission. On the right, you see depictions of the types of missions we're trying to enable across the solar system, such as Saturn probes, pinpoint landings, sample returns, etc. And these science missions are driven by the Planetary Decadal Survey, which was recently completed in early 2022. And this sets the science priorities for the next decade and shows us what mission targets we need to achieve. Assessing the state of the art of entry, descent, and landing for this wide range of science missions is a bit challenging because the EDL designs and systems are really specialized for each destination because it has unique environments and requirements depending on where we're going. We've put together a table in the middle of the page to kind of show all of the historical entry, descent, and landing missions and really what the new features of those were and what was new at the time, and then establish the state of the art going forward. The ones in the bottom of the table in purple are entry, descent, and landing missions that have not performed their EDL yet or are still in development. So these are the anticipated capabilities we expect them to have. You can see that the newer missions always build upon the previous missions and try to leverage that same technology, but they always try to squeeze in a little bit more performance and get more out of the systems. As we go forward, we see that we need to be more cognizant of our margins and how we protect against risk, because every bit of margin that we carry then impacts performance. Every kilogram of thermal protection system that we take over and above what we really need limits the science we can do or may bump us onto a larger launch vehicle and increase the cost of the mission. So really what we're trying to do here is enhance missions that we can do within our current technology and also enable new missions by developing a whole new capabilities. In the upper right, you see some of the pictures of the historical missions that we've flown to Mars, to Jupiter, and back to Earth. And then in the bottom right, you see the table of the historical Mars missions that have all leveraged the Viking heritage technology from the 1970s. In addition to our past missions, there are a number of technology investments over the past 15 years that really have established the state of the art and are being applied to current and future missions. One important area is thermal protection systems, which are critical to any entry system. We've made investments in three-dimensionally woven materials, which are very robust, such as heat and spiderweave material. We've also invested in advancing our phenolic impregnated carbon ablator, or PICA, which is really the workhorse of our Mars missions, derived from what was used on Stardust. In the parachute area, parachutes have been used for decades, but there's still a lot of uncertainty in their performance, particularly in supersonic flight regimes. We are working on modeling techniques to better understand the performance of parachutes, and we hope to apply that to future missions. Guidance, navigation, and control simulation is one other area of investment. Modeling and simulation is critical to entry, descent, and landing, since this is how we certify our vehicles, since we can't test them end-to-end on Earth. We are constantly upgrading our end-to-end simulations to be able to support the upcoming missions to new destinations in particular, and uncertainty quantification is one particular area of focus. In addition, we're looking at atmospheric models for those new destinations in the decadal survey where we haven't been before or don't have very good engineering level atmospheric models, such as Saturn, Uranus, Neptune, and Venus. And then finally, if we look at our system architectures, we've made investments in new areas that can enable missions of the future, such as deployable decelerators that package smaller than rigid aeroshells, either deployables like Adept or inflatables like HIADS. We are also looking at the effects of retropropulsion on the aerosciences performance of systems, as well as high impact, high reliability systems such as the Earth entry system of Mars sample return, which could be a platform for future low-cost systems. I mentioned that entry, descent, and landing modeling and simulation is critical to these planetary missions, and again, that's because we can't validate them end-to-end at Earth, and so we rely on our simulations to certify our systems before we put them on the launch vehicle. Now, this is extremely challenging because our models, in some cases, have undefined uncertainties because we don't have a lot of in situ validation data. So not understanding our margins really leads to difficult risk trades throughout the system development and can increase the cost and schedule. And then each of our missions tends to get more ambitious with time, and so we try to squeak out just a little more performance from these systems. So again, we need to understand our margins, and our models need to keep up with those more challenging conditions. And even if we think we're reflying a system, it's not actually a reflight because we're going through a different part of the atmosphere or to a more challenging location or with more mass to carry more science. And so again, we need to constantly evolve our models for these changing conditions. And then some of the most critical, challenging events along the entry, descent, and landing timeline have the worst models, such as parachute deployment, which wasn't modeled for years. We're just embarking on that now. Separation dynamics, TPS failure modes, backshell radiation, and these are all because we might have limitations in our computational capability, or we just don't yet understand the physics of that problem. So all of these areas need continued investment to make sure that we can really effectively execute these planetary missions of the future. To provide some idea of the range of missions that we're talking about for entry, descent, and landing, we look at the 2022 Planetary Decadal Survey. This page shows a list of the potential flagship missions that could be considered over the next decade or two. And I've noted the ones here that would potentially involve entry, descent, and landing, and which EDL capabilities might be enabling or enhancing for those missions. You can see that it's quite a broad range of missions, ranging from Uranus to Enceladus, where there's no atmosphere, to Mercury, to Venus. Then at the bottom of the page, we've listed the new frontiers 5, 6, and 7, those medium-sized missions that are on the potential proposal list for the next 3 cycles. And again, you can see that there's a wide range of missions that have entry, descent, and landing either at a planetary destination or back at Earth to return samples. At the bottom of the page, we've provided the link to that 2022 Planetary Decadal Survey for reference. So if we look at that list of challenging future science missions and assess that against our entry, descent, and landing state-of-the-art, we've identified 26 gaps that need to be closed to enable this outcome of planetary entry, descent, and landing. We've listed the high priority ones here in 4 categories: modeling and simulation, including uncertainty quantification; performance validation, which deals with sensors and instruments that can gather in situ data as well as unique data from testing on the ground. We also have EDL hardware technologies that can increase the reliability or improve the cost of future missions and enhance their performance. And then small spacecraft technologies, which can enable this emerging class of missions to accomplish real science through entry, descent, and landing. On the left, we list some of the recent and current investments towards these areas, and note that a lot of these are co-funded by the Science Mission Directorate. I'll also note that the precision landing technologies that are really very critical to a lot of these missions are covered in a different Envision Future Priorities package, dealing with landing within 50 meters precision and avoiding hazards. I'll note that for modeling and simulation, we very much depend on and use our university grant mechanisms, such as early stage innovation, early career faculty, and we have a new Space Technology Research Institute as well. And then in the hardware technologies area, we really leverage the small business and innovation research mechanisms to get in those technologies from the commercial sector that can help us close our hardware gaps. The next few charts in the package look at mission-specific applications, their challenges, and how EDL technologies will be infused to enhance or enable these missions. The first chart is about Mars sample return, which is a mission currently in development. It actually has 2 EDLs, the sample retrieval lander, which lands on Mars, and the Earth entry system that brings the Mars samples back to Earth. The sample retrieval lander has several challenges, as it's the heaviest vehicle we've ever landed. It has a large volume to accommodate the Mars ascent vehicle. It must land precisely, and it's a pallet-style lander, meaning not like a sky crane. It has nozzles underneath that could cause plume surface interactions. The Earth entry system is a Category 5 return vehicle, which means it must have high reliability and not fail upon entry or impact. It's released a few days before it arrives at Earth, and so it has the chance of micrometeoroid and orbital debris damage. It has extremely tight mass constraints because we have to take that mass all the way to Mars and all the way back, so it's a big lever arm. And then we have the G-sensitive payload, which is the Mars samples. On the right, you see several of the ways we'll infuse technologies into these missions, including enhancing models, commercializing sensors that could be used for precision landing, employing new materials, and again, using our end-to-end simulation capabilities. There's one entry system technology that's particularly well suited to the ice giant missions of the Planetary Decadal Survey, and that's aerocapture. Missions to Uranus and Neptune have very long trip times and are especially mass constrained. But an orbiter can use aerocapture which is using the planet's atmosphere to take up 95% of its arrival velocity, drastically reducing its propellant requirements, shortening the trip time, or enabling more science, such as multiple probes to increase the science return. Error capture's never been performed, but it relies on the same validation methods we use for current EDL systems, and it employs the hypersonic guidance that has been demonstrated on Apollo, Orion, and the recent Mars missions. We've invested in 3D woven thermal protection systems, which are extremely robust to the high entry speeds and are very insulative against the high heat loads of these long atmospheric passes. An Earth error capture demonstration would reduce the risk of this maneuver and prove out the advanced guidance and control methods that will be used on these challenging Neptune and Uranus missions. This chart details some of the challenges with aero capturing at these ice giant locations and our approach to infusing technologies to enable these missions. A couple challenges that haven't been mentioned yet are that we're traversing a hydrogen-helium atmosphere, so that brings us increased aerothermodynamic uncertainties, as well as atmospheric uncertainties, because the atmospheric structures of these outer planets are not understood as well as those of our close neighbors. To enable error capture will require advances in modeling and simulation, coupling of tools, and understanding uncertainties. Will also require developing those atmospheric models. As I said, performing an Earth error capture demonstration to reduce risk and mature the guidance and control. And then understanding how to apply our thermal protection system materials and their response to these new environments. To support the model validation, we want to make sure we instrument ongoing missions such as the sample retrieval lander at Mars and Titan's Dragonfly mission, as well as develop new low-cost instruments so that we can also instrument these ice giant missions and get engineering data for future model validation. The Planetary Decadal Survey calls for probes at these outer planet destinations, such as Saturn, Neptune, and Uranus. So we want to enable the EDL technologies to support those missions as well. Some of the challenges on the left are, again, flying through unknown atmospheres at very high velocity with new thermochemistry, understanding how the vehicle flies under a parachute and how the parachute deployment is going to perform, as well as the stability of these probes, which will be unguided. On the right-hand side, we have, again, some of our infusion approaches, which are to improve modeling, coupling, and validation, to perform ground testing, to anchor our models, as well as establishing the atmospheric models, understanding our woven thermal protection systems, and again, gathering as much in situ data that we can, even if it's from other destinations. This final chart of the package summarizes our forward plans for closing the high priority gaps that you've heard about. Again, on the left, we have the 4 categories of gaps, and on the right are our near to midterm plans. The green items are those that are current investments, and the yellow ones are yet to be funded. I've covered most of these throughout the video, but I wanted to call your attention to a few that I haven't touched on. In modeling and simulation, not only do we need to advance our constituent models, but we need to begin a retooling process to modernize our tools to be able to take advantage of high-performance computing architectures like GPUs and exascale as we couple tools and begin to look at more complex models in the future. Under performance validation, not only do we want to take full advantage of current and upcoming missions to gather in situ data, but we also need to make sure we keep our ground facilities healthy. You'll see one item there in white on a new Planetary aerothermodynamics facility. That's really outside the scope of a technology investment. It's an infrastructure item, but it's something that will enable us to maintain a state-of-the-art testing capability on the ground. In EDL hardware technologies, we need to maintain the thermal protection system materials that we've developed so far. We need to make sure that the supply chains are in place and that we have the expertise for when those materials actually come into use, because it could be several years. And then under small spacecraft, we want to make sure we can be creative and use all the mechanisms at our disposal to enable more frequent, low-cost missions of the future. The final chart of the package has an acronym list, so we invite you to refer to that. This concludes this video. Thank you for watching.